Yes, in our last class, we discussed about the lightly loaded bearing, the frictional force and the torque and power loss or power equation in the lightly loaded bearing. And today, we are going to discuss about the a pressure development in the hydrodynamic bearing. It may be full journal bearing or it may be partial journal bearing, okay, or it may be parallel surface or stationary surface, whatever it may be. So how the pressure is developed, okay. In the surveying the entire field of lubrication with its a main vital a physical and chemical manifestation, it seems that one phenomena that occurs most frequently and presently, and which probably as by a far most value, is the creation of load carrying dynamic fluid film. Fortunately for us, as a builders and users of machinery and mechanism of many kinds, this development of a hydrodynamic fluid film is quite a natural action and serves us obediently and tirelessly if given even the slightest encouragement. It is obvious that much of our industrial life would grind to stop without this lubrication phenomena. Every kilowatt of electricity produced by in the public utility is generated by machineries that operates on a hydrodynamic oil film. Every truck, tractor, bus, and other automobile runs as a result of this natural action in its bearing. And for thousands and thousands of other machines of every kind, this fundamental action is indissipable. The hydrodynamic theory of lubrication is based primarily upon a rather complicated mechanical analysis of the motion of liquid. Many of derivation for the various aspects of this theory can be extremely complicated and at not fortunate results of it lead themselves to very simple and understandable interpretations. So this dynamic hydrodynamic, I already explained what is meant by hydrodynamic. The hydrodynamic theory may also be used to design and analyze certain pumps, develop precision apparatus as being used to ruling engine of maintain a alignment of translating bed to with a few millionth of inches. It should be apparent that the range of application of hydrodynamic theory is very extensive indeed. It is of course required for the design and analysis countless type of bearing, and the theory can be a great value for applications not even remotely connected with bearing. Okay, so this hydrodynamic theory is a very important concept for applications of all the machineries and mechanisms. So here what we concentrating means how the pressure is developed in this hydrodynamic action. That is what we are going to discuss. Okay. So far what we discussed is what are the importance of hydrodynamic theory. And now we are going to discuss what is meant and how the pressure is developed. It may be any surfaces, maybe one is moving surface or one is stationary surface or maybe tapered surface, maybe parallel surface, whatever it may be. How it will generate the pressure and that pressure is capable to or sustain to carry the load. That is what most important. Okay, and here uh, there are so many types: thrust bearings, parallel journal bearings, and journal bearings. Okay, and first we discussed how the velocity and how the pressure is developed in two parallel surfaces separated by a liquid film. Okay, so for that, so consider a surface. So one is one surface and another surface, and this is a fixed or stationary surface, and this one is a moving surface or a plate with a velocity of u. Okay, and here it is a dash. A is a cross section, and here you can b and b dash. Say here the velocity, how the velocity distributed along the this gap between the moving and stationary surface is like this. The velocity is 0 or minimum at the stationary surface and maximum at the moving surface, because there is a perfect addition between the fluid and the surfaces. Okay, similarly same kind here, also same thing. Okay, and whatever the pressure and whatever the pressure distribution is, pressure is always like this. Pressure distribution is like this. The pressure is at the this surface. Let us consider this as a C dash. Here the pressure is maximum, and here at the entry minimum pressure, and at the exit it is also minimum pressure. This is a entry and exit. So here it is a minimum pressure and minimum pressure, but here there is a maximum pressure. This is how the pressure is distributing. It is a parabolic. Clear? In case of this is one is a moving plate and other one is stationary. Clear? And of course this gap is completely filled by a fluid film. Okay, with a viscosity mu. Similarly flow through in the non-parallel plates. So if it is non-parallel means this is a stationary plate, okay, or a plane thrust bearings, whatever it may be. So next condition is, if we consider a taper surface, that is what the taper or fixed shoes. We already discussed what is meant by fixed shoes, pivoted shoes, and plane surface. And here, if we consider a taper surface, that is what in the fixed shoes, the taper angle is fixed. Here, the pressure and the pressure development as well as the velocity distribution is also varies. Okay, that you can observe here. Yes. This is what the taper surface. Alpha is a stationary taper angle. Alpha is the stationary taper angle, is fixed. Okay. And here it will flow between inclined surface. That is what the taper surface. This is how it varies. It is a velocity. Okay. First consider A dash, B dash is the cross section. How the velocity. So here the velocity is more because the cross section goes on decreases, so it increases the velocity, and here the velocity is less. Okay, actually this is what the velocity, but originally this is what we expect, but practically this is what e c dash is the velocity, only a small velocity, so that there is a negative in the velocity. And pressure, of course, this is what the pressure distribution, and this is a load carrying, so exactly on the center there is a load carrying, so pressure is more. And you can see this is what the negative velocity and this is what the positive velocity, and here it is exactly same velocity. Okay, and this is what the pressure, so along the thickness of the fluid film, how the pressure is. Okay, and here the velocity increases, velocity decreases, because you just take an example, consider a water is flowing in the pipe. Okay, the water pipe is having a same cross section, but once we disturb the cross section by holding that pipe, it will change its velocity, correct? You can observe in that. So if you change the cross section by holding or by pressing the pipe, okay, the velocity of that water flow changes, it will increase because you change the cross section. Here also same concept, the fluid is flowing and we change the cross section so that it will develop the pressure. Okay, and the velocity is also changes, but it is not happens in the stationary plate. Here it is a stationary plate. Okay, both are parallel, so the velocity at the entry is equal to velocity at the exit. Okay, but here the velocity at the entry and exit is changes, and here it is more at the exit, and at the entry it is less because there is a more cross section, more area to enter, here less area to exit, so that velocity increases. And also it will affect the pressure. Okay, it will create the it will create means, because of this less in the area, so it will creates the back pressure. Okay, there is a rush in the fluid and it will creates the back pressure, and this back pressure will sustain or will able to develop the pressure, and that pressure will carry the load. Okay, and the development of this pressure is constant, means it is fixed, it is not changes, it is not changes with the with respect to the load. If the load whatever it may be, it will delivers the same pressure. Okay, so here, and these are the consider a non-parallel plates which is shown in the figure, in which one is stationary. Okay, one is stationary, and while the other is moving with a constant velocity in a direction shown, means left to right, as assuming the width to be large compared to the clearance, width is large compared to the clearance, flow perpendicular to the plate of, and this can be neglected, the volume of lubricant dragged into the space between the surface, this a dash, is greater than volume of lubricant which is discharged from the space b dash, assuming fluid to be incompressible. Of course this is a one important assumption, it is an incompressible, the volume of oil carried into the space must be equal to the volume discharged from the space. Therefore, the excess volume of oil carried into the space is squeezed out section between this A dash and B dash, producing the pressure induced flow. Because of this pressure developed in the oil film, and this capable to support the whatever the vertical or applied load on the bearing surface, and this alpha is always a constant. Okay, so this is what the how the pressure is developed. This is a fixed shoes. Of course, it's a fixed shoes. Means here the shoe taper angle is fixed. This is how pressure is developed. Is it clear? ಅರ್ಥ ಆಯ್ತಾ?
Yes, sir.
So next we move on to the how the partial journal bearing the pressure is developed. How in case of partial journal bearing the pressure is developed. This you can observe here. This is what the partial journal bearing, okay, the journal, and this is a bearing surface which is always less than the 180. The contact between journal and the bearing is less than 180. That's why it is called as a partial journal bearing. This is how pressure is distributed. The pressure means the oil film pressure. The oil film pressure here at the entry and exit is always minimum, okay, with a flow rate Q, but pressure is maximum here. This is a pressure maximum. The maximum pressure is, yes, this provides the maximum pressure, and the average pressure of the oil film P is equal to W by GL. So D is the diameter, W is the applied load, okay, and the L is the length. Yes, here you can see small r is the radius of the journal, okay, RB is the radius of the bearing, and here W is the vertical load which is applied on the journal, and E is the eccentricity between the journal center point and the bearing center point. It is always E, okay, and here at the entry A to C and discharge or exit B to D, and in between E to F cross section where the maximum pressure, here the maximum pressure is developed, and at the entry the velocity is less, there is a negative lack of velocity, okay, and here the velocity is more, this region is a positive velocity, means there is an excess of velocity at the exit, and at the entry there is a less velocity, there is a rush in the fluid, okay, because there is a cross section decreases here. When the cross section decreases, obviously velocity as well as the pressure increases. There is a flow back of the fluid and it will creates the pressure, and that pressure will capable to or sustain this vertical load, okay. It creates the converging and diverging cross section. It will divides entire this bearing surface into converging and diverging, and in the converging there is a decrease in the cross section. It may causes the pressure development. Here what we expect is negative, sorry, positive pressure, and in the diverging cross section there is an negative in the pressure. In the diverging the cross section goes on increases, it will decrease the pressure, so that it will a negative, uh, negative in the pressure, and here there is a cross section goes on decreases, it will increase the pressure. So here positive cross section pressure development, and here there is a negative pressure development, means pressure is goes on increasing and here pressure goes on decreasing, clear. And at the entry and exit there is a pressure is always constant, that is what atmospheric pressure. So this is how the pressure is developed in the partial journal bearing. And similarly come to the full journal bearing, how the pressure is developed in the full journal bearing. Yes, here you can see this is a full journal bearing, aerodynamic bearing. This is a bearing surface, and this is a journal center, and journal, this is a journal center and bearing center, okay. There is an eccentricity load is applied, and this is what the two surfaces separated by a thick layer and absorbed layer, and this is how the pressure is developed in full journal hydrodynamic bearing. Hydrodynamic means hydro means fluid, dynamic means spontaneously it will generate the pressure. Static means it need a external source of pressure. As this is the first initial position, here there is a oil inlet. It is at the rest position. Okay. The full journal bearing, the space between the journal and the bearing is filled with a liquid lubricant, and the journal is at rest. This is at rest, loaded by a vertical load W. In this case, there is a metal to metal contact between journal surface and bearing surface is at point. Here this is a point where there is a direct metal to metal contact between journal and the bearing surface. Okay. Yes. Here you can see the gap is completely filled by a fluid film, and this is a bearing surface and journal. Because of the load at rest, there is a direct contact, and there is an eccentricity is maximum. Eccentricity is maximum, and there is a direct contact. So here the journal is full journal bearing at clockwise direction. Here we consider a clockwise direction. Okay. The journal rotates slowly. The journal in the second figure, the journal rotates slowly in the direction, means clockwise direction. The journal rolls up. Yes, it will rolls up. It's a point contact M, and here it will roll up on the bearing surface due to the friction. There is a lot of friction between the journal and the bearing surface. Because of this friction, it will roll up into the new position called M. From here to here it will shift. Okay, it's a M position, and this roll up is because of friction. The point contact is now shifted to M. In this position, the speed is low, the pressure built up in the film can be neglected. Means the speed is low and the pressure developed, whatever the pressure is developed, it is neglected or very small. Extreme boundary condition is exist in this position. Extreme boundary condition means we already discussed there are three types of boundary conditions: thin film, thick film, and extreme boundary condition. Here the extreme boundary condition. In extreme boundary condition, there is a direct contact between the two surfaces. That is what here in the position M. Okay. The continuous oil film consists of two parts, and this continuous of oil film, it is a divided in two parts. One is a converging oil film. Okay, converging oil film, that is above the line. This is what this line here. If you make it this point as a L, so L to M is converging and M to L is diverging. Okay, and diverging below the line. Here it is a this line. If it is above the line is called converging, and below the line it is converging. L to M is called converging. M to L is called diverging. Or the speed increases slowly and pick up a positive pressure. Means when the speed is reaches maximum, and the speed is reaches maximum, and it will develop the pressure, and in the converging part which moves the journal to a next new position left side, means from here M2 it will shift it to new point called N. Means because of there is a converging and diverging, and there is a speed increases. Because of the speed increases, here also the flow in the fluid film is also increases. Yes, and this if the flow increases, there is a converging, gradually decreasing the cross section, and there is a rush in the fluid flow or the rate of flow, and it will creates the pressure. And here there is an accumulation of pressure, and this pressure will causes or shifted this point contact from M to N. Okay, when the speed of the journal reaches a certain level, sufficient pressure is built up, and converging part of the fluid film and the oil lift the journal and it will separate. Okay, and journal surface from the bearing surface is minimum thickness of the oil film, which is between the, as you can see, H minimum there. Here, when the sufficient enough of speed or pressure is developed, and that pressure is slowly will separates the journal to this bearing surface. Okay, and it will separate, and now it is operating under a boundary condition, thin film boundary condition. It is not a thick, it is operating under thin film boundary condition. Here H minimum is the minimum oil film thickness, and this is a maximum. Here it is a maximum and here it is minimum. So this minimum fluid film will separates the journal and bearing surface. Okay, it avoids the direct contact between bearing and the journal. Now the eccentricity will reduce to minimum, not zero, will reduce to minimum. Here in the first figure it is maximum E, and here in the fourth figure it is E is very less, because there is a gap or a small film which is between the two surfaces, that is what H minimum. So this happens, this mechanism happens only for a clockwise direction. If the same thing for the anti-clockwise means the first position is at rest, there is a direct contact where E is maximum. When the slowly the journal start rotating, it will shift to new position, roll up called M, okay, left side. Then the speed increases, it will shift it to new position from M to N to the right side. The previous from left side, but here shifted to right side. And once the sufficient pressure is developed because of converging and diverging uh, portion, so there separates and it is become H minimum. Okay, it is in the right side, here it is in the left side because of clockwise direction, here it is in the anti-clockwise direction. Okay, this is how the pressure is developed in a fluid film. So first rest condition, start to rotate, okay, then shift it back. And here you observe that, see, see here, the pressure is always maximum here. It's a converging part and diverging part. In converging part, pressure is positive pressure, means the cross section decreases, pressure increases. So here slowly the pressure is increases, but in the diverging part, cross section increases, the pressure goes on decreases. Okay, so here negative pressure and here it is positive pressure, because pressure is increasing, that's why positive, pressure is decreasing, that's why it is called negative pressure. In the converging positive, in the diverging negative. And because of this dynamic action, it will sustain or it will carry the whatever the load W acting on the journal surface. Is it clear? Yes, here also you can observe. Okay, and here oil valve continuously will supply the oil for this dynamic action. And this is at the rest, this is about to start, and this is at during running. At it, the speed is maximum. So in the examination, you may get question on pressure development in the full journal, partial journal, or parallel plates or taper plates. First, you have to write the neat figure, then you have to explain how the pressure is developed with respect to the velocity. Here I written the notes. Yes, theory part, these are the figure. You have to write neatly. Then here there is a explanation regarding that. Okay.